Hi everyone, and welcome to this mini session on system dynamics, which is a type of modelling you may remember from earlier in the course. We talked about where we can use system dynamics models to try and model large-scale systems and view the dynamics within that system. So we're going to be talking a little bit more about that in this session, and also showing you a piece of software called Insight Maker, which is a free and open source piece of online software that you don't need to install. You can just access in your browser that allows you to build system dynamic models. So I'm going to show you a really simple model, get you to build one, and then encourage you to sort of play around with that. So system dynamics is a modeling method in which the structures within a system, i.e. the individual components within that system and the way in which they relate to each other are captured. And the basic principle underpins all of system dynamics is that the structure of the system determines behavior. Um, and a good way to think about system dynamic systems is like a plumbing system. So imagine you've got a plumbing system where you've got water flowing around the system and flowing into various components, radiators, or whatever it may be within that system. And it's the rates of flow between different elements and the things that affect those rates of flow that we're really interested in. And so hopefully this will become a little easier to understand as we go through some of the examples. But where you're interested in flow from one component of a system to another and the dynamics of that flow and particular things that happen, system dynamics can be a really useful tool. So let's imagine, as an example, a really simple system that we'll all be familiar with. And that system is the chicken and the egg. So, in the chicken and egg system, chickens lay eggs. We also know that eggs hatch into chickens. The more chickens there are means more eggs are laid. And as more eggs are laid, we know that more chickens will hatch. I hope everyone's following along with this so far. I know this is quite complicated. So far we've described a chicken and egg system. And this system is an example of something known as a reinforcing loop. Now you'll learn a bit more about reinforcing loops and balancing loops when we come to talk about causal loop diagrams and qualitative system dynamics in the first problem structuring project proposal session. But for now, understand a reinforcing loop as being like a vicious circle or a virtuous circle where more chickens means more eggs, and then in turn more eggs means more chickens, and more chickens then means more eggs, etc. So you've got that reinforcing effect happening. And reinforcing loops and their counterpart balancing loops, which are is kind of the opposite, where as one thing increases, another decreases, and it balances a loop out. They are fundamental aspects within system dynamic models because they're usually where a lot of the interesting behavioural dynamics emerge. And we'll see that as we go on a little bit later. So, based on what we've talked about, and based on this very complex system of chickens and eggs, um, just take a moment to think about what kind of curve we might expect to see if we were to track the chicken population over time in this model. So, have a think about that. But whilst you do that, let's actually start thinking about how we might build a model to see what kind of curve we would get. And you may have already worked out what kind of curve, um, but let's model it as we do with all things. So in order to model it, we're going to use a piece of software called Insight Maker. This is an online piece of software, so you don't need to install anything. All you need is to access it through your browser. You do have to sign up for an account, but it's completely free of charge. And I would encourage you, if you haven't already, to pause the video and in a moment when I give you the link and do that. Insight Maker is a drag and drop based environment, so there's no coding, which I'm sure you will be delighted to hear, having spent many weeks in Python and a little bit in R as well. There's no coding involved, it's completely drag and drop. Um, And it allows us to construct system dynamics models. It does also allow you to create agent-based models. I haven't checked that out in full. Um, my advice would be to stick with Mesa if you were doing agent-based simulation models. This is primarily, Insight Maker is primarily designed for system dynamics. And as I mentioned, Insight Maker is completely free and open source. So in order to build a system dynamics model, we need to know what some of the key building blocks are. In the same way as when we built a discrete event simulation, we talked about the key sort of elements being processes and queues and entities flowing through those things and start points and end points, etc. And when we talked about agent-based simulation, we talked of agents and an environment and interactions, etc. Well, system dynamics has its own set of building blocks, the things that make up a system dynamics model. So one of the key building blocks in system dynamics is something known as a stock. And a stock holds the stuff, whatever it is, that's flowing around within the system. So imagine a water tank, and it's holding an amount of water that's flowing into and out of this tank. So that's what a stock is. So we might, for example, have a stock for eggs, which represent the number of eggs in our system. We've also got a thing called flows. Flows are the things that allow our stuff to move around the system from one stock into another, for example. And so you can imagine water flowing through pipes between these tanks that represent our stocks. And the rate at which stuff flows can be controlled by a valve. And so we can change the rate at which stuff flows around our system. And those rates at which things do flow around the system are usually very important in a system dynamics model. We've also got something called variables. You'll be well familiar with the concept of a variable in programming now. But in system dynamics, what we mean by a variable is something that's not otherwise captured by the model, but will influence either a stock's level or rate of flow into or out of a stock. So these are extra things that we want to capture that aren't otherwise captured, and we can in the Insight Maker we can easily make these user definable. So if you remember from Mesa, we set up for some of our variables, we set up sliders that allowed us to change those variable values as an end user. In Insight Maker, we can do this really, really easily just by saying, yes, we want the user to be able to change this. And we can set that on a variable. And you'll see how to do that. We've also got a concept of links. Links are things that link variables or other stocks with other elements. And they indicate that a stock's level or a flow rate is affected either by another stock's level or by one of the variables. So there's two kind of arrow type things in a system dynamics model. You've got the flow, which indicates the actual movement of your stuff, whatever it is, from one stock to another, and you've got the kind of dotted arrow, which represents a link. Now, so nothing's flowing along those links. It's just saying A over here influences B in some way, so that we can describe a flow rate or describe a stock level in terms of the elements that we're linking in. In some system dynamics building models, you'll also have the concept of a cloud. These are like entry and exit points in a discrete event simulation, where this is where sort of stuff comes into and out of being. In Insight Maker, there aren't clouds; things just pop in and pop out from nothingness, and we'll show you how that works. It's a little bit more fiddly, not very much, but it's a little bit more fiddly in Insight Maker, unfortunately. So let's now that you've got the sort of basics there, let's have a look at Insight Maker. So if you go to insightmaker.com, you'll be asked to log in. Obviously, if you haven't already created an account, this is the point at which you will need to do so. So just create your free account, pause the video whilst you do that. And then you'll be taken to your home screen. Now yours will be empty because obviously you haven't got any insights that you've generated, but this is where all your insights will be saved, and they get saved automatically. And we'll show you how that happens as long as you're connected online. One of the great things, if you do lose a connection, an internet connection in the middle of building an Insight Maker model, you'll still be able to carry on building the model. It's just that the model won't save until you get a reconnection to the internet, at which point you can then save it again. So the first thing to do, we're going to create a new insight. So if you click on this button up here, this will take you into a new insight. You'll get this thing that pops up whenever you create a new insight, which talks to you about some of the things you can do. Feel free to have a look at that another time, but for now, just click the "Click Me to clear this demo model" button, and then we've got a blank model. So this is where we're going to build our model, and I'm just going to take you through some of the key things that you'll want to look at if you're building an Insight Maker model. So up here in the top left, we've got a facility to add primitives. So if we click on that, it's a little drop-down list. Here's the sort of list of different things that we can add in, and they're split into 3 different groups. System dynamics type stuff, which is what we'll be using. Agent-based modeling type stuff. Again, don't worry about that for the moment, because that's only if you want to create agent-based models. And user interface stuff, so we can make a nice sort of user interface type thing, add buttons and text and pictures. But again, don't worry about that for the moment. In System Dynamics, you'll also see something called a converter here, which we haven't talked about. Don't worry about that. We're not going to be covering that today, but you can check that out at your leisure. But you'll see 2 of the key things that we were talking about, stocks and variables. So if I click Add Stock, you'll see it pops a stock straight into the window. I can move that around by left-clicking and dragging. If I double-click it, I can rename it, not stock, however I want, whatever I want to call that particular stock. I can do the same with variables. If I click variable, it brings a variable in, and I can double-click and rename that whatever I like. You'll see some information over on the right as well. Whenever we've got something, one of the primitives selected, various information comes over on the right. There's lots of useful stuff there. 2 of the things I'd particularly flag up first. One of the things, if you're in a stock, it'll have a little field here called Allow Negatives, and that will default to yes. Sometimes in a System Dynamics model, you want to capture there being a negative number of things within a stock. However, in reality, a lot of the time, you're probably not going to want to allow there to be negatives, i.e. if there are 0 in the system, you want there to be 0, and you don't want things to continue flowing out after 0. So usually you would want to change that to no. Similarly, in variables, so we've got here our variable. If I click on that, again, you get things pop up. There's one of these things here that says show value slider. By default, that's no. If I were to click yes, and then click off it, you'll see that variable value can now be changed by the user, and we'll get to practice at doing that later. So that's how easy it is to do in Insight Maker. Another thing just to flag up, so if we go back to the stock, I said to allow, usually you want to allow, not allow negatives, so we select no on that. Don't confuse that with this max and min constraint down here. So you may think, as I did when I first started using Insight Maker, that you might just simply want to select min constraint of yes and set that to 0 to constrain the system so that it can't have a value less than 0. And similarly, you can do the same with maximum constraints. Be careful about using that, because what that will then do is if the model tries to flow something out of a stock and there's nothing left, the model will stop, and it will stop at that point, and it'll say the constraint has been breached. That's usually not what you want. So usually you're going to basically just want to, you don't want negative values, so that's where you'd normally put it in there. So those are the sort of stocks and variables, but up here you'll also see we've got flows or transitions and links. So let's put in another stock here. I'm just going to call that stock B. And let's imagine we want to set up a flow between stock A and stock B, so things flow from A to B. By default, flows and transitions are selected, and you can see that's darker. But if not, just click on that. And then all you need to do, when you hover over the middle of a stock, you'll see that this little arrow appears. just left click, hold it down and drag to the stock you want to flow to, and it will create a flow automatically between, in this case, stock A and stock B. And in the same way, I can name that flow. Oops, let's try that again. So I can name that flow my flow. Let's do it up here, it might be a little bit easier. And so now we've got a flow set up between A and B. Now, the most important aspect over here of a flow is the rate of flow. You see by default the rate of flow is 0. So what that's saying is for every time unit in the model, flow 0 units of stuff from A to B. Obviously that's not very useful at the moment. If I go back to stock A, you'll also see one of the important points of any stock is this bit under allow negatives where it says initial value equals 0. Those are the initial amount of things that we want, whatever our stuff is, the units of stuff, the number of units that we want at the start of the model. Sometimes you may want 0, but other times you may want to start with a certain number. So let's just imagine we've got 10 units of stuff initially here. We'll start in stock B with 0 units, and I'm going to have a flow rate. I'm going to change my flow rate to 1 here. So what should now happen is that for every time unit in the model, 1 unit of stuff should flow from stock A to stock B. So if I click simulate up here, it'll automatically draw a graph, and you can see what happens in the green line here. The green line indicates the stock level of stock A, and the red line the stock level of stock B. And as we can see, very simply, we've told it to flow 1 unit from A to B per time unit, and so that's exactly what's happened. A starts off with 10 units, and then gradually over the course of 10 units goes down to 0, and stock B starts off at 0, but then because 1 unit is flowing into it from stock A at every time unit, then it gradually increases up to 10. And then after that, nothing changes because we've told the system not to allow negatives in stock A or stock B. And so once it gets to 0 in stock A, there's nothing left to flow over. So that's just a really simple example to show you how that works. Let's imagine that rather than having a set flow rate of 1 unit of stuff per time unit, that we wanted to make that a bit more complicated. So we might want to have that depend on a variable. So we've got our variable up here, and what I can do is I can click on links to indicate that I want the flow rate of my flow to be dependent on this variable. And so I can do the same as I did for a flow, except this time clicking links. Again, I hover over the variable, and if I left click and link into the thing I want to be influenced by that variable, in this case my flow, then you'll see it set up a link. So things aren't flowing in this case from variable to my flow. We're just saying variable will influence my flow, hence the dotted line. So let's set this variable to the value of 2. And then I'm going to change, if I click on my flow rate, rather than having a set flow rate of 1, if I click the drop down arrow here, I can go to an equation editor. So if I delete the 1 here, you can see that all the things that are linked into that flow, and by default the stocks from which it is coming and to which it is going, are automatically included as being things you can reference. Are listed down here, and it includes, because I've said that created a link between variable and this flow rate, I can now talk about that variable when I'm determining my flow rate, because I've said that the variable will play into this flow rate. So let's just imagine, really simply, that I want to say whatever that variable value is. So if I click on variable, I want that twice that variable value to be my flow rate. So if I click apply to that, we've now got a simple equation. So if I click simulate, as expected, we've got a new extra line here because it'll automatically add in extra primitives. I'll show you later how you can remove those. But that's just the value of variable, which is consistent at being 2. But you can see here, as we would expect, and before we had one unit of stuff per time unit leaving A and going to B. In this case, we've actually got something different happening. We've got that um, whatever value is in variable, and we've set it to be 2, twice that is going to leave A to go to B. That's what we've said will happen. So you can see here in a single time unit, at time 1, we start time 0. So at time 1, after one time unit has elapsed, stock A is now at a value of 6. 4 things have left stock A and consequently gone into stock B, exactly how we would imagine. That's a really simple example, but those are the basic principles for how you would then sort of build out your model. You'll see a save button up here as well. That's the first time you create an insight, you'll need to manually save by clicking save, and it'll then ask you to name that insight in some way. I won't for this one because it's just a little dummy one to show you what's happening. But you can choose whether to make it public or whether to make it private. If you make it public, anybody can sort of go in and play around with your model, and also what's known as clone it, so they can take a copy of your model and play with it in a very open source way. So we've already seen the simulate button up here, which runs the model. There's also a button up here called settings. Here we can set how long we want the simulation to run for, and we can also set to offset the start of the simulation by a certain amount of time, which can be useful. So at the moment it defaults to 20, but let's say I wanted to run that for 60, and then we can set down here what our time units represent. Now, for the purpose of the model, it doesn't really care as long as we're consistent, the same as in Mesa. We can have it represent anything, but let's say I wanted it to represent minutes, I can select minutes there, and so now my time model is in. My time units in the model are representing minutes, so I would run that for 60 minutes. And we can also set the step, so in increments of 1, and that's usually what you would want. So I'm just going to cancel that for the moment. Okay, so that's a kind of general introduction to Insight Maker. There are other elements within here as well. There's things in the edit menu, style menu, you can change styles, fill colours of your stocks and things like that. Lots of things that you can explore at your leisure, but those are some of the key elements. So what we're going to do now is to try and build this chicken and egg model. So I'm going to come out of this. I'm going to click the main Insight Maker button here. Let's click leave to that, and I'm going to create a brand new insight. Again, I'm going to clear that. So let's go back to our slides for a moment and think about what we're going to need to build our model. So in our model, we're going to need 2 stocks. We're going to need a chicken stock, no pun intended, and we're going to need a stock for eggs, because those are the 2 things that we want to keep count of: the number of chickens and the number of eggs. And we're going to start with 100 chickens and no eggs. So let's put that in first of all. So let's add in a stock here. Drag that there, and I'm going to call that chickens. And then let's add in another stock, which I'm just going to drag here. Doesn't matter too much where I put it, but I know what's coming. And I'm going to call this eggs. So now we've got a stock for chicken and a stock for eggs. And remember, we said we're going to start with 100 chickens and no eggs. So in our case, our stance on the old chicken, what came first, the chicken or egg? In our model, it's going to be the chickens that came first. There were no eggs. So if I click on the chicken stock, we want to change this initial value to 100. So we start with 100 chickens. And we'll leave eggs initial value as being 0. So now we've got a model where there's 100 chickens and no eggs, but not particularly an insightful model at this stage. So now we need to start capturing the flows here. So let's capture the first flow first, which is the easiest one, of eggs becoming chickens. Now, there is definitely a flow between eggs and chickens, because an egg becomes a chicken. So that egg, once that egg has hatched, it is no longer an egg for our purposes, and it then becomes a chicken. So it's a flow from eggs into chickens. So I'm going to create a flow from eggs into chickens. So I've got flow already selected here, and I'm going to select from eggs into chickens. And just because we're also going to have some other flows in here, I'm just going to left click on that flow, and I'm going to drag. If I go into the middle, you'll see a little arrow will appear there. I'm going to left click and drag so that we move that out, so that we can play around with stuff in the middle as well. You'll see, unfortunately, the name is independent. The name of the flow is independently attached. So if I left click on that, I can drag that across to wherever I want it. So I'm going to call this flow. It's always good to name your flow in the kind of present tense, because it's an action that is happening. So this flow, if we think about what that represents, is effectively the process of eggs hatching. So I'm going to call my flow eggs hatching because that's what that flow represents. It represents the flow from eggs to chickens, and that process is the process of eggs hatching. Now, the number of eggs that hatch, if we just go back here for a moment, if we assume that all of our eggs are fertilised for a moment, fertilised eggs take on average 21 days to hatch. Now, in our model, if we click on settings up here, I'm going to select to have our model run in weeks. So if we just click weeks and then click apply. So our time unit in our model is going to be in weeks. So everything that I'm going to describe is in weeks. So if it takes 21 days for an egg to hatch, we need to describe the flow rate from eggs to chickens in terms of how many eggs are hatched per week. So here's one of the first unusual things about system dynamics. It's something to get your head round. If an egg takes 3 weeks to hatch, in system dynamics world, that means that a third of an egg is hatched per week. So that after 3 weeks, a full egg is hatched. And that might seem odd, but that's how system dynamics works. And what it will do is it'll move a third of an egg from eggs to chickens per week. Now, obviously, in reality, that isn't how we would imagine things will work. But because what we're looking at is rates of flow and the emergent sort of dynamics that come from that within a system, then we're talking on a continuous spectrum. And so that's how we would describe eggs hatching in our model. So if I click on eggs hatching here, we need to define the flow rate. So if I click on the little arrow, so we can go into the equation. So remember we said that eggs hatching is essentially if one egg takes 3 weeks to hatch, then a third of an egg would be hatched per week. But of course that's just for one egg, and so we're likely going to have more than one egg, and so the number of eggs that flow from being eggs into being chickens per week would also depend on the number of eggs. So effectively what we're saying is, well, one egg would be, one third of an egg would be hatched per week. And that would apply for every egg. So we could write 1/3 in brackets like this, 1/3 times by the number of eggs. And that would be correct. But if you remember your sort of simple fractions from school, you remember that that's the equivalent of saying eggs divided by 3. Because we're effectively saying 1/3 times by eggs over 1. And so we simplify that to eggs over 3. If you find it easier, if that makes no sense to you, or you can't get your head around that, and you want to write 1/3 times the number of eggs, that's absolutely fine. It'll work in exactly the same way. But just make sure you put the brackets around the 1/3, or you'll to indicate that needs to be done first. Otherwise, you'll run into problems. So eggs over 3 is what I'm going to write. So if I click apply, that will say for each egg, a third of it should hatch per week. So we've captured the flow from eggs into chickens, that the flow being eggs hatching into chickens. But of course we also need to capture the other flow in our system, which is the flow from chickens into eggs. Now, so this is the flow where essentially chickens are laying eggs. Now, it might be tempting on first inspection to say, well, that's easy. I will just add in a flow from chickens to eggs. But that would be wrong. And the reason that would be wrong is because it is not true to say, unlike with eggs, where we said it's true that an egg flows from being an egg into a chicken for the purposes of our model. But it is not true to say that a chicken ceases to be a chicken and turns into an egg when it lays an egg. At least, not in any chickens I've seen. What's actually happening is that chickens lay multiple eggs, um, and the number of chickens will, of course, influence the number of eggs that come into being, uh, because we've already said that the more chickens there are, the more eggs are being laid. But it is not true that chickens flow into eggs. And so we need to do something a little bit different here. So what we're actually saying is that eggs are coming into being and chickens, the number of chickens are influencing that. So we need eggs to come into being from nothingness. And we talked about the concept of a cloud, which isn't in Insight Maker. So what we have to do, if we want to flow eggs in from nothingness, then in Insight Maker we need to first add in a dummy primitive, a dummy stock. So I'm just going to put a stock here. I'm going to create a flow into eggs, and then I'm going to delete the stock that it came from. And what that is now doing is that flow is coming in from nothingness. These are new eggs that are coming into being. So what this flow represents is eggs being laid. So I'm going to call my flow the laying of eggs. So they're coming in from nothingness, but of course we've said that chickens, the number of chickens, is going to influence the rate at which eggs are being laid. So we turn to our links. So if I click links, and then if I click on chickens, the chicken stock, and drag down to the flow laying of eggs, that now says, right, the laying of eggs flow is in part determined by the number of chickens. So we're now going to need to specify what that flow rate should be. So let's just turn back to our slides. And we know that chickens lay, on average, 5 eggs per week. So for every chicken, we're going to assume that a chicken lays 5 eggs. Now, you'll remember from our previous training in discrete event and agent-based simulation that we said, well, you don't use the average. You need to capture variability within a model. In system dynamics, that goes out the window because we're focusing on sort of flow dynamics. We only capture those average values. We don't capture any variability in that. A system dynamics model is an example of a deterministic model where every time you run the model, the same result will happen. And that's because there's no randomness within that model. So if chickens on average lay 5 eggs a week, we'll assume that each chicken lays 5 eggs a week. So if we click on laying of eggs, our flow here, and then click on the flow rate, the little arrow here, our equation is actually quite simple because if it was just one chicken, the flow rate would be 5, but it'll be 5 per chicken. So we're going to say 5 times by, and I can click on chickens here because I've linked in the stock level of chickens to say that the stock level in chickens is going to be used in this equation. And I can click chickens to say it's 5 times the number of chickens. So for every chicken, there will be 5 eggs coming into being per time unit per week. Week is our time unit. So if there are 4 chickens, then there will be 20. 4 chickens at a particular time unit. There will be 20 eggs on that time unit being coming into being. So 5 times chickens. So now we've set up our chicken and egg model. We've got 100 chickens to start. We've got 0 eggs. We've got our eggs hatching into chickens, so flow from eggs into chickens, and that being a third of an egg per egg that is flowing from eggs into chickens per week. And in terms of eggs coming into being laid by our chickens, then 5 eggs are coming into being per chicken per week. We've actually completed our simple chicken and egg model. So if I click simulate now, we can see what happens. So those of you who guessed that this was an exponential curve that you would expect to see would be correct. because what we're seeing is huge increases over time in terms of the chicken and egg population. So the blue line here represents the number of eggs, and the green line represents our number of chickens. And we can see there are huge increases over time. And it looks as though not much is happening in terms of increases over here, but that's because the graph is automatically scaled to the highest value that it will reach within our time. So over the course of 20 weeks, our eggs have gone from being 0. Within the first 5 weeks, we've got over 8,500 eggs. By 15 weeks, we've then got over nearly 17 million eggs, and so on and so on. And that's increasing and increasing and increasing, as we would expect to see in an exponential curve like this. So we are clearly being overrun by both chickens and eggs. Just for completeness, we said that we were going to run this over the course of a year. So if I go back into my settings for the model, and I can click up here where it says simulation length, we've already defined that we're talking in weeks for each time unit. So if I click 52 weeks, it will represent a year. Click apply, click simulate. We'll see the same thing happening, but obviously on a much higher scale now, because that scale has now hugely increased, because it's automatically scaled to what's going to happen after 52 weeks. And we saw how many chickens and eggs there were even after 20 weeks. But we see the same effect happening here. Something to flag up here. By default, it'll add in the default display will be to show a graph monitoring all the elements that we've added in to our model. I can actually select different displays. So I can click Add Display. I can select to add a display that's a table. So rather than showing a graph, it'll show the numbers over time. So if I click on that and click Apply, and then, oops, sorry. What I should have done, if I go into Table, I also need to specify the data that I want to display. So if I click on that and say I want to monitor both the number of chickens and the number of eggs over time, click Apply. Then we can see that we start with 100 chickens and 0 eggs at time 0, time 1, 100 chickens, but now we've got 500 eggs because we said that each chicken would lay 5 eggs per week. So 500 eggs have been laid after 1 week. Then we've got 266 chickens because some of those eggs have now hatched. A third of the 500 eggs have now hatched, and now we've got 833 eggs, etc., etc., etc. And you can see so clearly how these numbers increase massively. And these numbers up here, if you're not familiar with scientific notation, that basically means 7.59 times 10 to the power of 18. So 10 times 10 times 10 times 10 times 10, 18 times, and then times by 7.59. So a huge number of chickens and eggs here. So you can really see that clearly. I can also add in a display if I wanted to have a scatter plot, or if I just wanted to keep that time series, but I only wanted to, for example, to display the number of chickens. I can click that, and it'll just show me based on the number of chickens. So you can have various different displays, and you can name those displays different things in this title field here to make them sensible. And you can click delete on any of those to remove them, which is quite useful when you have lots of them here. So that's going to be really useful for us. So it's time for you, I think, to do an exercise. So what I want you to do is to, if you haven't already, make sure you've built that model, so follow along with those instructions. But then I want you to adapt that model to capture the following dynamics. So I want you to capture the fact that not all eggs are going to be fertilised. And I want you to make the proportion of eggs that are fertilised a user-definable variable. So remember we said that any of our variables in our model, so if I just put a variable in, a dummy one here, if I click the show value slider thing on here and click yes, it'll automatically make that a user-definable variable. So then we can specify the value of that variable simply by selecting values on that slider. So I want you to make that a user-definable variable. As a clue, we don't need in our model to model unfertilized eggs. So if you change the egg stock name to fertilized eggs and let that guide your thinking, So that will hopefully give you a clue as to where you need to use this new variable of the proportion of eggs that are fertilized, i.e. think about eggs coming into being. We're going to assume by default that 80% of eggs are fertilized, but again, we'll make that a user-definable variable so that that can be changed. I also want you to capture the fact that chickens can die through predation from foxes. We're going to assume in our model that chickens don't die through natural causes and the foxes don't die through natural causes, but we are going to capture the fact that foxes will unfortunately kill chickens. So you're going to need to model foxes in your model as well. We know that a fox gives birth to around 5 kits, baby foxes, per year. And I want you to start with 100 foxes in your model. And we're going to make an initial assumption that each fox kills one chicken every 5 weeks, or in system dynamics terms, every fox is going to kill zero point 0.2 of a chicken per week. Because remember, we have that continuous flow in our model. So you're going to need to make the number of chickens that are killed per fox per week a user-definable variable. So that 0.2 will be the default, but you make that a user-definable variable. And that killing rate of foxes killing chickens, number of chickens that are killed by foxes per week, is going to influence a flow out of chickens, because chickens are now also going to flow out into nothingness when they are killed through predation. So once you've built that model, I want you to then use that model to determine how many chickens you think would need to be killed by each fox each week in order to make the chicken species extinct within a year. I should just point out, because this sounds quite morbid, I have nothing against chickens or foxes. I love all animals equally. But for the purposes of this exercise, it's quite useful to show you how one aspect of a system dynamics model will influence another aspect of that. So remember, you're going to need to capture foxes coming into being in the model, and the rate at which foxes come into being will be determined by both the number of kits each fox gives birth to, and also the number of foxes. If there are more foxes, there are more kits being born. And you're going to then need to say that the number of foxes is going to influence a flow out of chickens, representing chickens dying through predation in the way that we've described there. So have a go at that. Have a go at building that model. Let me know if you have any questions. And in part two, in the part two video, I will talk you through the solution. What I'd also like you to do, and to be thinking about as you're building this model, is some areas of policing that you think system dynamics could be really useful in. So much in the same way we talked about for MESA expanding out from the disease outbreak model to applications policing, I want you to think about potential applications for system dynamics models in policing. And in our webinar, we're going to, at the start of the day, we're going to be talking about some of these ideas. So I want you all to come up with some ideas, and we'll have a general sort of 10-minute discussion at the start, just to share some of those ideas and see what some of your thoughts are in terms of how system dynamics might be used for applications in policing. So for now, have a go at that exercise. Let me know if you get stuck or have any questions, and have fun. And then once you want to look at the solution, just look at part 2 of the video. See you shortly.